All right, next big topic that we're going to talk about in class is going to be shear. And this is shear on a reinforced concrete beam. Now, for those of you that have taken structural steel design, how long did you talk about steel or shear in steel beams? Hardly at all, right? Because it wasn't that big of a deal. Well, we'll spend a couple plus weeks on shear and reinforced concrete, and just by the amount of time that we spend on it relative to steel beams, you should recognize it's an important topic. All right? Shear, if we go back to strength of materials, we said, hey, we have a beam, and the beam, if I look at a certain section of that beam, there's a, depending upon the loads that are on the beam up to that section, we could say the shear on that section is the sum of the forces. That was the definition of shear at a particular location. So if this was, 1,000 pounds up, and the only other force you had on there was 300 pounds down, at this section there'd be a shear force of 700 pounds up. Okay? That's what we learned in strength of materials. Now, we didn't do that much other than to introduce shear in strength of materials, because we came up with this concept of developing a shear diagram. Okay? So our shear diagram would look like this. Again, shear diagram is simply the sum of the forces, but we'd say, oh, if this was 1,000 pounds, I'd go up to 1,000, and then nothing would happen until I hit this load, and if this was 300 down, it'd drop me down to 700, and if nothing else happened up to this point, at that point I'd have 700 pounds of shear. Okay? That's what the shear diagram was all about. Okay, so that's what we did back in strength of materials. In concrete, reinforced concrete beams, what you got to understand about shear and why it's such a big deal is that section of a beam, any beam, has to resist that shear force. 700 pounds, 7,000 pounds, 70,000 pounds, whatever it is. It has to resist that shear force. The way on a beam that it's going to resist that shear force, if this was our beam, and then we thought, hey, we're going to look at a little element of concrete. If I had 700 pounds up on this section, that little piece of concrete is going to have to resist a portion of that 700 pounds. There's going to be a shear stress developed at that, the little piece of concrete is going to develop an incremental resistance to that shear. Well, if that happens on that piece of concrete, on the other side of that little piece of concrete, there has to be a corresponding stress, right? Same, equal and opposite stress. But on that little piece of concrete, you can't just have vertical shear stresses. You got to have corresponding equal and opposite horizontal shear stresses, right? So this little piece of concrete that we just picked out at this section has vertical shear stresses on it and has these also horizontal shear stresses on it. They're all going to be equal, right? So that means if I have this force of 100 acting down and this force has to be equal 100 acting to the right, it's going to give me a resultant that combines, just like you can combine X and Y components, and that resultant is going to be acting down to the right. Same thing's going to happen over here. I'm going to have a resultant that acts up to the left. What angle do you think that acts at? 45. Now, imagine this little piece of concrete, little square of concrete, and I got these diagonal forces What are these diagonal forces doing at the corners? How are they acting? Tension. That's a little piece of concrete. Concrete's not real good in tension, is it? Where's it going to crack? It's going to crack perpendicular to that. Okay? That crack, that's going to act perpendicular to these diagonal tension forces. Shear actually creates a type of tension in a concrete beam. Okay? The crack that would be associated with shear in a concrete beam is going to be at a 45-degree angle. If you ever are out there in the field and you're, you got a project under construction, you got concrete that's a day old, a week old, a month old, or even if you're in a structure and it's 20 years old. You ever see a beam with a diagonal crack in it? Okay? Especially in the regions of high shear, close to the support, that's dangerous. That's telling you something. Okay? That's something to really put up a red flag about. Shear cracking is not like bending cracking. Bending cracking, is going to take place because our beams are supposed to be ductile. Bending cracking is going to take place, if it's a ductile beam, sort of a slow, progressive manner. Shear crack, if it occurs, is going to occur very quickly. And it literally will run on a 45-degree line. It'll probably split the beam down here where the longitudinal steel is, and it'll run up to the top of the beam, and literally it'll break this chunk away from this chunk, and the beam will be, literally ready to collapse. And it will occur in seconds, or maybe less than a second. That's how, that's what I always tell people, hey, I've done a lot of inspection and whatnot, consulting, going into old buildings and whatnot. I've seen one shear crack in my whole life in a real structure. Okay? Because most people that see shear cracks in beams are already on the ground. Okay? So it's a fast type of failure, catastrophic type of failure that we've got to be concerned about. And it's because literally it's a tension type failure. Concrete's not very good with tension. Okay? So again, shear in concrete beams, serious type of behavior. We have to be on guard against it. What do you think we do? What do you think we do to try to reinforce our beam against the shear? Huh?
Extra steel.
Okay, extra steel, but what type of steel? Well, remember, we've already talked about this, but remember in our beam, the first couple of weeks we talked about this steel, the primary bending steel. But there's also this other steel that's going to be a U-shaped bar. It's called a stirrup. Well, that stirrup's going to occur at intervals. Okay? Well, guess what? If I've got a stirrup here and maybe another stirrup down there, what are those stirrups going to do? They're going to try to keep the beam together. Because as this thing tries to pull diagonally and cause the crack this way, if I've got this steel anchored in the piece down here, the piece of the beam that's down here, the piece of the beam that's up here, what's this stirrup actually going to be placed into? Tension. And it's steel. And steel's good in tension. Okay? So these U-shaped bars called stirrups, this is the way that we, reinforce our beam against shear. All right? So, sort of the, you know, a little bit of an intro to shear, the behavior we're going to see, and then ultimately how we're going to reinforce against it.